right? So today we will talk about the real Jordan form.
Wait a minute.
So, yeah, so since we couldn't meet the other day, we'll meet today. So this should wrap up the course, I think. All right, so let me,
Complex or?
oh, this is the abstract algebra.
Okay.
Do you not have things to write on?
No, it's okay.
Do you need paper? I got paper. I'm sorry, I should have warned you.
I brought the wrong book.
My bad. No, since Jade couldn't come today anyway, and I was just going to do something researchy, I thought, well, why don't we, try to wrap up the other thing. Okay, so here's the deal. If we have t, all right, is a linear transformation from v to v, where v is a vector space over the reals, all right, then we can define like t from the complexification of v to the complexification of v via t of x plus iy equal to t of x plus I t of y. All right, and here the complexification of v sub c is what it is x plus iy such that x and y are elements of v. And I've explained that technically you can look at that as C tensor v, all right? But we don't need the sophistication of that for this lecture. It's sufficient to say this: the scalar multiplication v sub c is this. If I have, a plus ib times x plus iy, I get ax minus by plus I times bx plus ay. All right. So that defines the scalar multiplication of v sub c. So you could look at it this way. So this makes v sub c a vector space over the complexes. Okay, it's a complex vector space. All right, and well, that's pretty good. See, because we can argue that there's a connection between the matrix of. So we can prove theorems connecting like the basis for the real vector space V to the corresponding basis for the complex vector VC. So like one of the theorems is just this: if beta equal to v1 v2 vn basis for v, then beta is basis for v sub c. And the proof of that is relatively simple. I mean, if we have, x plus iy, you could write that as the sum of x sub I, v sub I, plus I times the sum of, y sub I, v sub I, which then you can write those sums together as the sum of x sub I plus I, y sub I. Maybe I should be using j's. AI is square root of minus 1 here, right? So sum over x sub j plus iy sub j times v sub j, right? But that is an element of the complex span of beta. So beta is a spanning set for the complexification. And then we can prove linear independence over the complex numbers through similar arguments, right? Okay, so if we have a basis for v, that's also a basis for v sub c. And what about the other direction?
If you have basis for v sub c, is that basis for v?
Right, can we...
And what'd you do with the standards? Take the real component?
That's the question, is how can we get from a basis for v sub c to a basis for v? How exactly is that accomplished? Well, let's see here. So let me be a little bit more concrete about all that. Let's look at the specific case of a two-dimensional vector space. All right. So let's look at the dimension of, v equals to 2. All right. So this is the dimension over the reals, right? That means that the dimension over the complexes of the complexification of v will also be equal to 2. All right? And specifically, I want to look at, suppose we have a linear transformation from this v to v. All right? And I want to suppose we have an eigenvector, right? I want to suppose that the complexification of t, all right, which maybe I should slap a t sub c on it. Let me do something. Let me call this t tilde. Okay? So like t tilde of x plus iy is like that. This notation is actually used in engineering a fair amount. They'll slap a tilde on things to talk about like the complexification of the variable. It's not an uncommon notation actually in engineering, especially like EE. So t tilde from the complexification of v to the complexification of c, and I want to suppose that we have an eigenvector. So let's say v equal to x plus iy, not equal to 0, and t tilde of v equals to lambda v, where lambda is not just any eigenvalue, it's alpha plus I beta, where beta is not equal to 0. And of course I'm assuming alpha and beta are real. Okay, so we have a genuine complex eigenvector with complex eigenvalue lambda. All right? And I'm assuming that x and y are the real parts and imaginary parts of the vector v. So here, x and y are elements of v, and alpha and beta are elements of the reals. So what I want to unwrap here for us is, what does it mean? Okay, so first of all, we're assuming that t is a mapping from v to v, right? So t tilde is the complexification of that mapping. That means something specific about the complex eigenvalue. So check this out. So we have t tilde of v equals to lambda v, right? So you can take the complex conjugate of that, which I'm going to use a star for in this lecture because it's easier to see. So if I take the complex conjugate of this, in other words, I have t of x plus I t of y, right, equals to, what is this here? Take the complex conjugate of all that. And then I take the complex conjugate of lambda times v. All right, through straightforward properties of complex conjugation, since t of x and t of y are both real, that means that they complex conjugate to themselves again. the I goes to minus I. All right? And the other side, we get, lambda conjugate V conjugate, right?
Yeah, but isn't V real too?
No, V is not real. V is the complex, V is a complex eigenvector.
Okay.
And we can prove that V cannot be real.
Because I think lambda, it has its choices. Well, I think in here we actually define it.
Well, yeah, I should say I'm assuming beta is not equal to 0 here, right?
Yeah. So the lambda has to have a conjugate.
Yeah, so that means beta being non-zero means that lambda and lambda conjugate are distinct.
Yeah.
They're distinct eigenvalues, which means that the vector which I'm about to write down, namely t tilde of x minus iy, that is t tilde of v star, and that's equal to lambda star v star, right? So let me say the sentence. Lambda is not equal to lambda star, right?
Yeah. Well, we knew that from the V not being equal to
Lambda is not equal, that's true, that was apparent already. Lambda is not equal to lambda star because beta is not 0.
Yeah.
Thus, eigenvector, V for lambda is linearly independent from V star for lambda star. Because they're distinct eigenvalues. We prove that linearly independent distinct eigenvalues give you linearly independent eigenvectors. And that means then that we can't have the vector v just be real. Or just be imaginary, because in either one of those cases, that would mean that v and v star are linearly dependent in the complex sense. One would just be a multiple of the other, a scalar multiple of the other. So, yeah, this gives us a couple different things, actually. So what data do we have to work with? We find thus, v star linearly independent, and both x and y non-zero, in V. Now, what's the matrix of T with respect to the matrix of T tilde, right? With respect to the basis, let's call this basis beta. All right. With respect to the beta, beta's a bad choice. Gamma, let's say gamma, okay? There we go. With respect to this basis gamma, what's it look like? It's diagonal, right? Because this is an eigenbasis. And the diagonals are lambda and lambda conjugate. So the matrix of this, if there is a complex eigenvector for the complexification, right, of a matrix of a transformation on a two-dimensional vector space, then it is necessary that that's a diagonalized transfer. The complexification has to be diagonalized, just like that. Now the question is, what is the corresponding? Can we find a corresponding form for the matrix of the original T back in the real vector space using this data? So what would be a natural choice? What could we try for? What would be a good choice for the basis?
Of V?
Yeah, what would be basis? Yeah, the basis for V. What should we try?
Basing it off that matrix.
Yeah, based on the data that we have, we've got our vector V. Really, the only thing we have that sticks out here is the x and the y, right?
Yeah. I mean, would you just do an x comma y type thing? But that doesn't make sense either.
Well,
Well, I guess it does because x and y are both the two two-dimensional, like they're both in dimensions.
right? X and Y are the right size.
Yeah.
They're two-dimensional vector. So yeah, let's try.
Like x0, y0.
Let me call this. Oh, here. Let me finish the tildification of all this. Gamma tilde. There. Tildes for everyone. So let's try gamma equal to x comma y as basis for v, over R, right? That makes sense. These are both real vectors, right?
Yeah.
Okay, so we need to figure out, so what do we have? We have that t, remember, how did all this start? This all started with t tilde of v equals to lambda v, right? So let's make that a little bit more explicit. What we're really saying is that t of x plus I t of y is equal to alpha plus I beta, right, times x plus iy. Multiply that out. What does it give you? It gives you alpha x minus beta y plus I times, beta x plus alpha y. Now this equation is in the complexification, right?
Yeah.
This is all happening in the complexification. In the complexification, one of the fundamental ingredients is that we can equate the real part to the real part and the imaginary part to the imaginary part. That's part of the construction. So here, this equation right here gives me two equations, namely that t of x is alpha x minus beta y, but also that t of y is equal to beta x plus alpha y. Right?
Yeah.
And so what this shows me is that the matrix of T with respect to this gamma basis that we just invented is what? So like this is T of x, right?
Yeah, is it like alpha x plus beta y?
Here, I'll write down one more step. Yeah, alpha x minus beta y. We need to find the gamma coordinates of that, right? And then beta x plus alpha y, find the gamma coordinates of that. What is that equal to, though?
With respect to the gamma would be like, no, that would be like 0.
So remember, the first basis member is x. The second one is y. So
Alpha, beta, alpha?
yeah, this would be alpha
Minus beta.
minus beta, right? First column, and then beta.
Alpha, or alpha.
Beta alpha. Yeah.
Which, yeah, that was to be expected though, right?
Well, that's to be derived. We just derived it. See, this is what's called the real Jordan block, right?
Yeah.
Of alpha plus I beta. So this is what I call the real Jordan form. Not just me, there's others. But they're relatively hard to find in the literature, I think. More hard than they should be. Goodness gracious. More people should be concerned about the interplay between complex and reals. So many abstract mathematicians are always just working over the complex numbers and they say, oh, well, you can figure things out if you look at the reals. Well, yeah, maybe I can, but what about the engineers? Give them something to look at. Don't I don't know, because, pet peeve of mine. So anyway, this is the real Jordan form. That is basically the signature of something having a real transformation on a two-dimensional space. If the matrix looks like this, that means that it's not diagonalizable. However, if we complexify the transformation, it's diagonalizable. And working back, we can look at the matrix like this. What is this matrix? Well, this matrix, if you divide out 1 over alpha squared plus beta squared, or excuse me, if you factor out alpha squared plus beta squared, like that. And then this is like alpha over alpha squared plus beta squared, beta over alpha squared plus beta squared, minus beta over alpha squared plus beta squared, alpha over alpha squared plus beta squared. All right. So this we could look at as a matrix, let's say big R. And if you calculate the determinant of that matrix R, you'll get alpha squared. I did it wrong. So I need a square root. A square root here, and a square root there, a square root everywhere. There we go. All better. So now if we calculate the determinant, we'll get alpha squared over the square root of alpha squared plus beta squared squared plus beta squared over the square root of alpha squared plus beta squared squared, which is alpha squared plus beta squared over alpha squared plus beta squared, also known as 1. So it's determinant 1. And also, you can check this. It's pretty easy to check that R transpose R is equal to the identity. So what that means is that this matrix that I've just written there is actually a rotation matrix. You can make alpha over S squared of alpha squared plus beta squared equal to like a cosine of theta. You can choose theta such that R is equal to cos theta, sine theta, minus sine theta, cosine theta.
Okay, so we're spitting back the results that we know.
Yeah.
But we're going from different, okay.
So my point to you is that if there is a complex eigenvalue for a real transformation, what that means is that there's a two-dimensional plane for the vector space in which you're working, on which, when you restrict the transformation to that two-dimensional plane, it behaves as a rotation paired with a dilation. See, this is not just a rotation, it's also multiplication by this number, but it's a dilation and a rotation. That's what the complex eigenvector eigenvalue corresponds to.
Okay, so it's a dilation by its modulus and a rotation by the argument.
Right. So now I just did it for a two-dimensional vector space, right? But you can see that this calculation will extend if we had like more than one complex eigenvector. What we can do is, well, here, let me just give you an example. Oh, thanks. So like example 1, if you'll forgive me if I don't show you the whole theory of it, but if I had, like t of v1 equal to 2 plus I times v1, and I had t of v2 equal to, minus 3i v2, and here v1 was, let's say, x1 plus iy1, and v2 was x2 plus iy2, right? In order for all of this to happen, t must be a transformation on at least a four-dimensional vector space. So let's suppose that, t is in fact a transformation from v to v, where the dimension of v is equal to 4. All right. Well then, the real dimension. So real dimension 4 can support two complex eigenvectors, right? Remember that since t is a real transformation, I'm assuming that means that there are actually 4 linearly independent complex eigenvectors, which diagonalize the complexification of this matrix. So like with respect to the basis, gamma tilde equal to v1, v1 star, v2, v2 star. We're not really that interested in this, but for the sake of complete discussion here, So the matrix of the complexification with respect to this gamma tilde basis would be a 4 by 4 matrix. It's diagonal. It's got 2 plus I, 2 minus I, minus 3I, and 3I. All right. With respect, then, this is, for the complexification of T. But the matrix of T, with respect to the gamma basis, where here gamma is what? It is x1, y1, x2, y2. So you just list out the real, imaginary of your corresponding complex eigenvalues, vectors, rather. And so that's going to give me basically the real Jordan block for 2 plus I up here. And then the real Jordan block for minus 3I down here, which is specifically I've already forgotten my formula. So 2, 1, minus 1, 2. And for minus 3I, you got yourself a 0, minus 3, 3, 0. Zero's off. And this is an example of the real Jordan form.
So for however many complex eigenvalues we have, we get like another set of 2 dimensions essentially.
Yeah, something like that. Let me look at a slightly more complicated example. If you had T, let's keep with the 4 dimensions, yeah? So if you had T going from V to V, dimension of V equal to 4, and suppose that you had T of V1 equals to lambda V1, and then you had T of V2 equals to lambda V2 plus V1. So that is a sneaky way of saying the chain condition. That's T minus lambda V2 equal to V1, yeah? Okay. So in other words, I'm saying suppose that, and I really, to stick with my notation today, I should say T tilde. Now in practice, people don't write the tilde on the T. They just say in Word somewhere, consider the complexification of the transformation. And then they use the same symbol for the transformation and the original one. And that's okay, but beware that mathematically speaking, it's great. So then, how's this go? Let's see here. So what happens this time, and we're going to assume, that, V1 is x1 plus iy1, V2 is x2 plus iy2, and lambda is alpha plus I beta, with beta not 0. All right?
So, we'd still have to write our gamma basis, right? Which the first part would stay the same.
Oh, yeah.
V1 conjugate.
Yeah, let's keep gamma still x1, y1, x2, y2. Let's list out the real and imaginary parts of our complex vectors to form the corresponding real basis of note. And let's just take a second here. What is T tilde of V? Let's call this equation 1 and equation 2. What do we equate? Equation 1 we've already studied, right? That's that T of x1 plus I T of y1 is equal to, how did it go? Alpha x1 minus beta y1 plus I times beta x1 plus alpha y1, right? That same calculation we just did on the other board. 2 is a little bit different, but not that different, really. How does 2 go?
We would have... But we also have the
right? The lambda v2 goes just the same, right? So we have, alpha x2 minus beta y2 plus I times beta x2 plus alpha y2, right? But then plus the v1 term, right? Which is just plain plus x1 plus iy1, right? So then what we need to do is take this equation, right? And equate the real and imaginary parts to find out what the equations are for t of x2. Like t of x2 is what? It's alpha x2 minus beta y1 plus x1, right?
Yeah.
And t of y2, what is it?
T of y2 is beta x plus alpha y2 plus y1.
Plus y1, right? So now we have all the things we need to figure out what's the matrix of t with respect to the gamma basis, right? So now remember, gamma is x1, y1, x2, y2, right? So first of all, x1 and y1, same song and dance, right? It's alpha minus beta. There's no x2 or y2 there, right? So it's just alpha minus beta, 0, 0 for column 1. Column 2 would be the coordinates of t of y1, right? Which are beta alpha, and then zeros, because there's no x2 or y2 in the formula for t.
And then the next one would
y1.
be alpha x2.
Well, yeah, the question is, what is the coordinate vector of t of x2 with respect to the gamma basis? I'll write it here before I write it in the matrix. So look at this. The first thing, what's the coefficient of the first thing in the basis? First thing in the basis is x1.
Yeah.
So the first thing here goes as 1. Is there any y1 here?
Yeah, beta.
There is, but that's just because I'm an idiot. This is supposed to be 2.
So yeah, 0 and then alpha minus beta.
Thank you, yeah. All right, so we'll put that down here. We got 1, 0, alpha minus beta.
Okay. And then for the next one, we have 0,
Uh-huh,
1,
yep,
beta,
yep.
alpha.
Mm-hmm.
Okay, so we now don't have 2 blocks, we have just a block of zeros.
So yeah, what we have now is, I call this like J2, maybe I put the R up here or something, I don't know. Alpha plus I beta. So this is the complex, this is the repeated complex, how can I say this? It's the real Jordan form corresponding to when we have a 2-chain of complex eigenvectors for the complexification.
This just keeps going no matter how many chains you tack on.
Yeah.
It's messier, but it just...
Right. I mean, I think, now here's where here's where, there's a 50-50 chance I'm right here, okay? So this may be the real Jordan block of alpha plus I beta tensor with 0, 1, no, that's not quite it. It's, yeah. Sorry. Just a second here. There's a way of expressing this as a tensor. I think it's, I want to say it's the identity, the 2x2 identity tensor with the Jordan block. And then plus the identity tensor, the 2x2 nilpotent. So I've either got it, it's either this or it's the same thing with the tensors, the opposite order. I keep forgetting. I always do this at the end of the semester and it never gets drilled into my brain to fix my conventional ambiguities, and at this point I've lost where my notes are. So the point is that this basically just sticks this matrix at the 1 and the 1 spot.
Because of the dimension and how the eigenvectors, like how the characteristic equation works out, you can only have like n minus 1 chains, right, per dimension.
Per dimension.
Like this can't have more than 3 chain.
For dimension 4, we could have a 4-chain of real eigenvalue. We could have a real eigenvalue, a 4-chain for a real eigenvalue.
Okay.
And then the matrix in that case would look like, you know, lambda, 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 1's on the super diagonal.
Yeah.
That would be what I call J4 lambda, where lambda's, you know, real.
Okay.
That's just a plain old Jordan block.
Yeah. Okay, so it can have as many chains as it has roots in the characteristic equation.
Can have as many chains as it has roots in the characteristic equation. It can have more than that.
Okay.
Because for a single root, we could have multiple chains. It's like you could have an eigenvalue of 3, and you might have, you know, 3. You might have 2 lone eigenvectors sitting out there by their lonesome, and you might have a 5-chain with eigenvalue 3.
Yeah, that's what we did last time. We saw
So,
like how it broke down.
Yeah, the number, I would say the number of distinct chains
Yeah.
is the number of linearly independent eigenvectors for that eigenvalue.
Yeah, I remember. If you had like an 8-dimensional thing, you could have like a 5-chain, 3-chain, and 1-chain.
Right, right. Let's see here if I have any explicit example for you. But that pretty much completes the story of, you know, how we find, so if we have a real transformation, right, what you do is you find all the real eigenvalues, right, and then you find the biggest generalized eigenvectors that you can. You find enough chains to fill up that part of the story, right? And then that gives you blocks for your, when you use that part of the basis, those blocks correspond to real Jordan blocks. Then whatever's left over, it must be that those are coming from the complex eigenvalues. The reason I can say this is that if we have a real transformation, we can always look at the complexification. The thing about the complexification is, because the characteristic equation for the complexified transformation is in over the complex numbers, that means that it splits. There have to be, by the fundamental theorem of algebra, n solutions to the characteristic equation of the complexification. So whatever eigenvalues we're missing for the original transformation over the reals, they're there for the complexified one. But the cost is that we don't get eigenvectors for the original transformation. We get you know, pairs of basis vector, which corresponds to planes in which the transformation operates as like a rotation and dilation, or something. I'm not sure what geometrically this is exactly. It's not quite that. It's something else. But in fact, geometrically, what is exactly this? I haven't really committed to explaining that. But I think it's something like a projection. It's like a slanted projection, something like that. So that completes the story, see, because if we have a real transformation, we can find all the real generalized eigenvectors together with the complex generalized eigenvectors, and then we just rip off the real and imaginary parts of those. What could be simpler than that? You just rip off the real and imaginary parts of them, string that all together, and then the resulting matrix is the real Jordan form, which is a direct sum of Jordan blocks and complex Jordan blocks, like I've been showing today. And this works for any real transformation.
Yeah.
So if you can prove something about the real Jordan form, then you've proved it for an arbitrary transformation. For example, what's the trace? What's the trace of an arbitrary transformation? So what's the trace of, you know, the kth Jordan block of lambda, where lambda is real? You got lambdas, right? K of them. One's on the superdiagonal. Who cares? The answer is k times lambda. Because you just add together lambda k times. That's the trace, right? Add the sum of the diagonals. What's the trace of, you know, like the real Jordan block? And suppose we're looking at like the, well, we'll just start out with the 2 by 2 one. What's the trace of that? Oops. Looks like it's 2 alpha, right? Think about this, though. This comes from lambda alpha plus I beta and lambda star equal to alpha minus I beta being quote-unquote complex eigenvalues for our transformation, right? What happens when you add the lambda plus lambda star?
You get 2 alpha.
2 alpha, right? So the sum of the eigenvalues is 2 alpha. The sum of the eigenvalues for the k block is k times lambda, right? So you can generalize this. You can look at an arbitrary Jordan form, right? And you can easily bootstrap this argument and see the trace of the Jordan form, right, of some matrix T, let's say, is equal to a sum of lambda, you know, let's say lambda j, where that's just a sum over all the real and complex eigenvalues. So the trace is the sum of the eigenvalues. And that still is true when your real transformation doesn't actually have eigenvalues for part of it.
Okay.
See, real mathematicians, elegant mathematicians who refuse to look at complexification, its interplay with the reals, can't say this kind of thing, unless they get into much more harder things that students wouldn't follow probably. But anyway, I don't know. So the trace is the sum of the eigenvalues. That continues to be true when they're complex. And the determinant, right? What's the determinant, by the way, in this block? Do you see it?
Of the k.
It's
Alpha squared plus beta squared.
right, but that is, notice, lambda times lambda star. It's the product of the eigenvalues.
Yeah.
That continues to be true. If you look at this one, you've got the product of the eigenvalues is alpha squared plus beta squared squared, which is, by the way, lambda times lambda times lambda star times lambda star. It's the product of the eigenvalues, complex eigenvalues for the real matrix. And it's even more obvious that the determinant is the product of the diagonals. See, if you look at the real Jordan form, if all the eigenvalues are real, the diagonal is just eigenvalues, right?
Yeah, we know from like the thing that if it's an upper triangular, like you can just take the determinant is just a diagonal anyway.
Exactly. So, but this is a general formula. The determinant is the product of the eigenvalues. Trace is the sum, determinant's the product. These we can prove by just explicitly looking at the Jordan form. And then the thing is, any matrix is similar to its Jordan form, its real Jordan form.
Yeah.
So because how does that similarity accomplished? You make a P which is formed from concatenating the Jordan basis, or generalized, the Jordan basis and the real imaginary things like I was talking about today. You can concatenate all those together to make the basis matrix. And then you multiply by the inverse of that, the matrix of your transformation times the basis matrix again, and that will give you the real Jordan form for the matrix. And since trace and determinant are invariant under similarity, if we can calculate the trace and determinant for the Jordan form, we've calculated them for the matrix period. And there are other arguments besides this which can be made in this fashion. So this is a very significant and powerful tool of matrix analysis, which everyone should know. Hey, this is why I haven't been able to find my calculator for like a week. It's been in this bag. Haha. Now the semester's complete. Anyway.